Hello. So, I created two videos, right? One improv. This is all improv, basically. And of course, I made multiple videos because it's improvisation. So, I will often make mistakes. So, I made one video last night, and I just made another video 20 minutes ago. Thank God my dog interrupted me because the first half of the video was pretty confusing and I didn't like it. So we're going to redo that first part of the video to transition to the next one. And this is more of a preface to kind of get you understanding. So I expect you to watch, no, I don't want it. But expanding upon what I said previously of a metric space, right? So when I said, so the thing about metric spaces and topological spaces, right, is that with an arbitrary metric and stuff, in a way, these can be the same. Not only in terms of basis, I'm going to tell you what basis means later, but just in terms of a metric space, or my bad. Let me just remove the dotted. I don't know why I put the dotted lines. So a circle can be the same thing as a square in a sense in a metric space, like with a certain metric. In addition to this, another reason, right, is in terms of basis, which I will tell you. So first of all, I want to get this out of the way. A vector space kind of gives you coordinates. It tells you the direction and position relative to a point, right? And that's what it does to a space. A metric just kind of cares about length and distance from 2 points, right? Doesn't really care about this distance or position with respect to this point and stuff. It just really cares about distance. And why? Why do we even care about metric space? Well, not only for the sake of generalization, but because most geometric objects are actually not vector spaces, right? So, or subspaces. So Rn, which we'll define as the set of all, I always ordered pairs, x1 all the way to xn, such that xi is in R, right? So basically vectors, right, with each component of that vector being a real number, right? Basically just think of this as a part of that set and stuff. If we have a subspace of it, like a sphere, right, or circle even, it's not a vector space, right? You could test this out for yourself, right? Notice how we one of the fundamental properties of vector space is it's closed, which means, so if it has addition and multiplication of scalars, right? So if a vector a plus b, right, if a vector is in a vector space, right, and beta is in a vector space, then these also must be in a vector space. And if that's in a vector space and this scalar, right, of that vector space, right, or kind of number, basically, we have to have that in that vector space. So you can kind of look at this already. Just apply that property and you'll see, right, if we add 0, 1 and 1, 0 to each other, which is this point and this point, it's going to be equal to 1, 1, right? And already it's not in there. And if we multiply it by a scalar, it's just only one point's gonna kind of come to there. So this is not a subspace and stuff. So, and another intuition for this, notice how it's curved, right? Vector spaces look at things linearly, which is like this. This is a linear graph. It's just x. It's a straight, no curved, and it's no curves basically and stuff. And this is useful in calculus, right? We have to look at derivatives, right, and integrals of curves, right? How do we do that without a vector space? And more in particularly, differential geometry or manifold theory. So when we look at any curve, right? Like this is what we look at. This, my shirt, anything around you, we look at, right? And we're like, how do we kind of understand this, right? Because it's not a vector space, so we need a metric space to kind of look at it, right? We need that approach. So now, a topological space, what it cares about is not kind of like just an object and stuff. It kind of looks at the space itself and the properties. Because like I said, a circle is kind of like a square, right? Or an open disk, we'll call this, is kind of like an open square. And here's another way to say it. These two generate the same space. So what does that mean? Well, so we notice that in a vector space, right? You could look at 3 Blue 1 Brown's video for this. I'm not going to explain it all. In a vector space, these two vectors, I hat and j hat, span R2. They create it. Basically, all possible linear combinations of this. So we think of a vector here, a vector here, a vector here, and we just think of it, just every single thing kind of glued together to create this. And it's the same thing, it's a very similar thing in a metric space and stuff. So we just kind of think of it as open disk, right? Think of this open disk. Think of this open disk. Think of this open disk. Think of all, like, just, I'm going to create a bunch of open disks, and all of this, and I'm going to represent also, I want you to note, I'm going to just basically call this board R2, right? Think of this board, think of this extending infinitely, think of this extending infinitely, think of the bottom part going infinitely, already you can kind of see that, and think of this part going infinitely. If I just put an infinite amount of open disks, right, on that board and stuff, and glue them to every single possible one, glue them together, that creates R2, and that's what we're looking at. And the thing about it is it doesn't matter if you use a circle or a square or a disc or a square and stuff. They create the same space, and that is kind of what we're looking at here. We're looking at how do we create a space, okay? I want to look instead at a space now. Let's just, and it doesn't even have to be R. Let's generalize it. Let's go further, right? Let's look at the space of integers. Let's look at the space of quaternions. Let's look at the space of rationals. Let's look at an arbitrary space, non-Hausdorff space. Let's look at everything, right? That's what we're looking at here. We're kind of extending it from Rn, right? And the reason why we extend it from Rn is because, well, what's interesting about not doing that, right? Why do you even care and stuff? This is basically kind of going into, again, I guess a lot of people debate this, but I would say definitely that math is kind of still grounded in the physical world. However, it may be abstract, but all of those abstractions still come from one thing, okay? You can't say that, oh, if we had I'm sure there's reality and stuff where everything is just different and stuff, and I'm sure we would probably have a lot different mathematics if we were in a different world. Everything, R2, kind of R3, basically describes where we live and stuff. So this is why kind of we fix it and stuff. And it has certain properties, right? And we want to preserve those properties and stuff. We want to preserve the properties of R2 that doesn't include distance. We don't care about distance. We just want to include certain properties of R2. What are those properties then? What properties create R2, and what can we make out of it and stuff? And how do we look at a mathematical space in terms of its basis of what creates it, and how do we look at the properties of that mathematical space instead of doing algebra or calculus on it? We've already done algebra and calculus on it. Now let's just look at the space itself and see what we can get from it. Let's see where we can go. And that's what a kind of the intuition for a topological space is and stuff. It's not the definition isn't arbitrary and stuff. It's still grounded and stuff. It's just I want to kind of talk about other stuff. And I mentioned previously like about a homeomorphism, right? This is probably the biggest concept in topology that everybody talks about and stuff. And without topology, we wouldn't really care about homeomorphism and stuff, and it wouldn't be as concrete and stuff. Because a homeomorphism, alright, it's just a function between two spaces such that that function is continuous. F, the inverse of the function, no, my bad. Ooh, is it? Yeah, right. The inverse function is continuous. And F is bijective. It's on two, basically. It's 1-to-1 and on two. And you definitely should know this by now. Okay, I'm not gonna teach you if you don't know this. So that's what a homeomorphism is, basically. And that's really what people should tell you what a homeomorphism is instead of all the other bullcrap and stuff. It's pretty intuitive by its own standard and stuff. So I don't know why people just make a big deal of it. X is a topological space, Y is a topological space. So let's look at a topological space and stuff. And first of all, how do we define continuity without length? How do we define, and how do we define, and this morphism and stuff doesn't really care about, it doesn't really care about any metric space laws or any vector space laws. Like a morphism is just something how we generate, like kind of map something to another thing. Like you could think of sine of x as a homeomorphism, right? This, you could think of it as the real line, r, right? This is how we just express the real line, and we're just kind of creating a bunch of curves on it and stuff. This is a terrible drawing of sine of x. There we go. And we're kind of bending it. That's what sine of x is really and stuff. And it doesn't care about metric. Do you notice that? Doesn't care. Doesn't care at all. Mm-hmm. Of course, if we restrict the map, though, I won't get into that. You can find that out over here. So, what is a topological space? So, first of all, to define a topological space, we need a set, and we need to define a topology. A set is basically just a bunch of objects, and we call it, a set's just determined by a bunch of objects. So, you could think of it as a box with, I don't know, anything. This marker, my foot, this picture of Michael Spivak, your mother, this, anything really. So that's really what a set is and stuff, and that's also why we care and stuff. It can contain anything. It doesn't even have to be numbers. Okay, so now we have to define a topology on X, and we can kind of think of a topology as something that transforms X or morphs X, which is what I said before. It's a function of X, right? So it kind of takes everything from the set X and then it creates a new set with everything in it, right? So that's what a topology on X is. So now we define those properties.